Hello and welcome to lecture 7. Today we're going to talk about linear transformations with domain R, and in the second part we're going to talk about the span of a tuple. So to start here, let us fix some notation. What we're going to do now is we want to look at linear transformations with domain R, and by R I mean here R to the n. And so we're looking at these following transformations gamma alpha, and what we can do is we can fix here some tuple of vectors in a vector space V and many, and then this will code a linear transformation from Rn to V, where I'm just gonna let the image of a tuple lambda 1 through lambda n be the linear combination of the given tuple in alpha v1 v through vn with coefficients lambda 1 through lambda m. So this is the right hand side here. Okay, and so just as before, sometimes we want to worry what is with n is equal to 0, could that be allowed? And so in this case, well, if n is equal to 0, then your domain is R to the 0, which can be identified with just the trivial set containing 0, and then alpha can be the empty tuple, and gamma alpha in this case will just be interpreted as the inclusion of 0 into the vector space where 0 gets mapped to 0. Okay, so let us get to our first theorem here, theorem 4.9. And so a priori we don't know that what we defined there was linear. Yeah, we just defined a function, and so the first thing we want to prove here is that that actually defines a linear function here. So what do we need to do? Well, we'll take two elements in R to the n, and we take a scalar in R, and then let's look at what happens if I apply gamma of alpha here to lambda x1 through xn plus y1 through yn. Well, let us put it into one element of R to the n. So we have here lambda x1 plus y1, let's say lambda x2 plus y2, and then go on until lambda xn plus yn. And now by the definition of gamma alpha, because alpha is this tuple v1 through vn, we get that this is equal to, well, the first element in this element of R to the n times the vector v1 plus, and let's also put the second one down, scalar multiplication with v2 all the way up to, well, lambda xn plus yn times vn. And now I can regroup, so this becomes lambda times x1 times scalar multiplication with v1 all the way up to xn scalar multiplication vn. So this takes care of all the terms up there that include a lambda, and then we get y1 scalar multiple v1 plus all the way up to yn vn. So it's just about regrouping, and then we'll see that this is actually lambda gamma alpha of x1 through xn plus gamma alpha of v1 through vn, and this is precisely what we wanted. So this ends the proof up here. So these type of linear transformations are going to be very, very important, and they're going to come up a lot. So this notation up here you should really keep in mind. Yeah, so I will refer to gamma alpha throughout the lecture and will pop up a lot. And the reason is that this is kind of the prototype of linear transformation that you can have in specifically when you have domain R to the n. And this is what we're going to prove next. So we're going to prove that actually any linear transformation looks like a gamma alpha for some choice alpha. But before we do that, we have to introduce some more notation. So what we're doing here is introducing certain vectors in Rn, and we're going to call them EI. And so the EI vector is precisely the vector that has a 1 in the ith position and a 0 everywhere else. And this will become very important when we introduce bases. The only thing we have to be a little bit careful is that EI, like the element, does depend on the context. Yeah. So E1 in R2 is the element 1, 0. But when I look at E1 in R3, it's going to be the element 1, 0, 0. And so obviously these two do not coincide. They're not the same. But we do, however, refer to both of them as E1. So normally it should be clear from the context what you want, but sometimes you have to specify where you take your EI from. So just be a little bit careful about that. And now before we go on, remark 4.10 here. So what I want to point out is that I can actually look at every element in R to the n as a linear combination of these EIs. So note that if I look at x1, xn, this arbitrary element in R to the n, then I can actually write this element as the following. Well, x1 times e1 plus x2 times e2 plus all the way up to xn times en. Yeah, so what do I really do here is, well, this first here takes care of the first coordinate. Yeah, what is x1 times e1? Well, it's the vector x1 and then a lot of zeros. What is this vector? Well, this is 0, x2 and then a lot of zeros. All the way up to, and this vector is what 0, all the way up to, and then xn in the last one. So pretty much on the right hand side, you just add up vectors which have one coordinate that is different from 0 and everything else is 0, and this coordinate coincides with the one on the left. And so this will be useful in the following. So let us see what we want to do here. So we want to prove this theorem, and as I said, this theorem now will tell us that basically, well, every t, so given an arbitrary linear transformation, this t is going to be equal to a certain gamma alpha. So we just have to choose this alpha wisely, and the way we do it is actually, well, each of these elements in alpha, these vectors in alpha, are going to be images of some ej. Okay, so in particular, vj, so the jth vector in this tuple should be t of ej. So let's prove this. So how do we prove that two linear transformations are the same? We do it in a way that we show that they coincide on every element. So now, for all x1 through xn in R to the n, we have that. Okay, let's start with t on the left-hand side. Okay, and this is where I'm going to use this remark from before, so I'm scrolling up a little bit so you can see it. So we're going to replace now x1 through xn by the right hand side of the equation up there. So by x1 times e1 plus all the way up to xn times en. Well, next we can use that t is linear. So we can pull the t inside. And so how did that help us? Excuse me. Well, the problem was that here, having t of an arbitrary element, we could not really compare it with the VIs or the VJs, yeah, because the only thing we know about VJ is that it's the image of the EIs. So what we really we had to modify this expression in order to, well, get an expression that really depends only on the things we know. And what are the things we know? Well, the images of the EJs. And this is precisely what we got here, because now this is by choice of the VJ. We have that this is precisely, well, x1 times v1 plus all the way up to xn times vn, okay? But then this is now by definition of gamma alpha, and alpha being here v1 through vn, this is precisely gamma alpha of x1 through xn. And so this finishes the proof. So now we have shown that if you take your alpha to be the images of the vectors e1 through en, then the linear transformation with domain Rn actually coincides with this gamma alpha here. So let's go to the next remark. So suppose here that you have some vectors v1 through vn in R to the n, and let A be the m times n matrix given by these VJs. And so we want to compare now the linear transformation gamma alpha, with alpha being the tuple v1 through vn, and the linear transformation given by A, which we denoted by TA. So first recall that T of A from Rn to Rm defined by x being mapped to ax, this is a linear transformation. And we also have that well, let's look at gamma subscript v1 through vn. So the gamma given by this v1 through vn there, which is, well, a linear transformation going from Rm to Rm. From Rn. Sorry. This was correct. This should be an M. Defined as, an x1 through xn gets mapped to x1 v1 plus all the way up to xn vn. Then one can check that these coincide. So I highly recommend to you to check that by yourself. And this is just true by matrix vector multiplication. Yeah, so this is somehow a different way of coding the exact same linear transformation here. And so what we want to do now is, well, if this is the way to code it, then, well, now this means if I actually, on top of restricting the domain to R to the m, but also restricting the codomain to R to the m, then, well, this will tell us that every linear transformation in this way actually should look like, Well, a TA. And this is precisely what the corollary says. And so what you want to say here is not only they exist in A, but they exist a unique one. And so now this comes to a new proof strategy. So the new proof strategy is to show that there is a unique such that. Okay? And there's always, it comes in two parts. Well, first it says there is something like this. And so this is what you usually want to show first. Because, well, if you want to show there is a unique thing, if you show there's only one, first you would want to show there exists at least one. Yeah. So first you show it exists. And then secondly, you want to show that it's unique. And I will get a little bit more into detail on how to show that something is unique. Great. So, as I said, it comes in two parts. So let's start with existence. For j in 1 through n, let Vj be equal to T of Ej. So as before in the proof of the T being equal to gamma alpha. And so now let alpha be equal to the tuple given by these Vj's, so V1 through Vn here. And then A should be the matrix again with the columns given by Vi. And A be the matrix with jth column given by Vj. And so now we just put the remark and the theorem 411 together. So first, theorem 411 ensures that T is actually equal to gamma alpha. Yeah, this is what we've just proven. Yeah, go back here. That here, so 411. That if alpha is equal to the V1 Vj, then T is actually equal to gamma alpha. So this is precisely how we've chosen Vj here. So this is the first part. And now the second part is that the remark before, so remark 412 gives that T of A is equal to gamma alpha. And so this implies now that T is actually equal to T of A. Okay, great. So we showed there is such a matrix. And now the second part is we want to show uniqueness. So we want to show there's only one. And this usually goes always the same way. So what we do is we're going to take two and assume for both of them both of them work. And then we have to show that they have to be the same. So suppose A and B are matrices over R of size m times n, and that T of A is actually equal to T of B. Okay, and now we want to show A is actually equal to B. So how do you show that two matrices are the same? Well, one way of doing it is showing that each and every entry is the same. But what we're actually going to show here is that each and every column is the same. So now for j in 1 through n, we have that. Well, let's look at the jth column of A. Okay. So how can I pick out the jth column of A? What I can do is I can actually multiply A times the vector Ej. So Ej is again the vector that has a bunch of zeros and a 1 in J. And so now if you think about it, well, how does matrix multiplication works? It takes a row of A, let's say the first row, times EJ. Well, since EJ has only a 1 in the jth coordinate, well, it picks out, well, the jth entry of the first row. Okay, so that means what? It means, well, the first entry of the jth column. Let's go on. What's then? You take the second row times EJ. Again, you multiply times a bunch of zeros and 1, which is in the jth position. So it's going to pick out, well, the jth entry of the second row, meaning, well, the second entry of the jth column of A, and so on and so forth. Okay, well, now this by definition is just TA applied to EJ. Yeah. Then, well, T of A and T of B coincide, so this is T of B of EJ. And then we're doing everything backwards. This by definition is B times EJ. And then this, as argued before with A, this is just the jth column of B. And we're done here. So thus, A is equal to B. Okay, great. So next, well, we want to talk about bases. So this is the big chapter 5 in the lecture notes. We're not going to get there today, but we're going to start talking about the span. And what we're really interested in is look at this gamma here, alpha. Yeah, I'm not going to go into details into the notation as before. And the question now is well, when is this surjective? So under which condition is this linear transformation surjective? Yeah, and so this is kind of the reason why I started talking about transformation before start talking about bases, although in the book it's in the other way around. The reason is because I kind of want to go back and forth in this way. So we're going to take here these gamma alphas as our default linear transformations, and we want to kind of go back and forth. What does it mean to be surjective? What does it mean to be injective? What does it mean to be bijective? And we want to find a condition on this tuple alpha v1 through vn. So you want to say something about this. Okay, so that's on the wrong page. Let's scroll down. So back here. This is the definition of what is a span. So we want to define what is the span of a tuple. So given a tuple v1 through vn in a vector space, then the span of this tuple is just the collection of all linear combinations in that tuple v. And then some conventions here. Again, we want to just know what happens when I have the empty tuple, and so the empty tuple will just span the zero vector space. And another convention is that if we want to say that a tuple spans a vector space if and only if the span of the tuple is the vector space, which is the same as saying that every element in V is a linear combination of that tuple. So before we go on, let's look first at some examples. Number 1. Let n be in the natural numbers. Then if we look at these elements that we talked about before, the EIs, they span R to the n. Let's go on. Let's look at the tuple maybe E1, E1 plus E2, E2 with E1 and E2 in R2 here. They span, then alpha spans R2. Let's look, let's take 1 x3 in the polynomials well, then the span of 1x squared is equal to, well, the polynomials of degree at most 2. So let's say ax plus bx plus c with a, b, c in R. So let's point out some basic facts here that are immediate from the definition. So let's give an n-tuple of vectors. Then we have the following conditions. First of all, V in V is a linear combination of this tuple if and only if it's in the span of the tuple. This is, I think I already kind of mentioned that when I introduced the definition. One more thing here. If I write if and only if and I don't type it out and I want to kind of shorten it, what I often do is write if with a double F. So I'm not misspelling something here, which I certainly have done in lectures before. This was actually intentional, and it's a short form of saying if and only if. Another thing that will come up and will be useful is that if you throw in the 0 vector, it doesn't do anything to the span. So if you add here 0v, then this is the same as the span of v1 through vn. And then last but not least, v1 through vn spans v if and only if, so again this double f, if the span of them is all v. Yeah, so it's just a different way of talking about it. More things here to note is that if you look at the span of this element, this is precisely the image of gamma alpha, where alpha is this given by v1 through n. This is precisely, no, it's precisely incorrect, precisely the image of gamma subscript v1 through vn. Yeah, so this gamma that we talked before. And so this already implies that span of v1 through vn is actually a subspace of v. Yeah, so there's lots of things that come out here. How do we do it in this way? Well, we showed before that the image of any linear map is a subspace, and since we identified this as being the image of a linear map, we just showed that gamma of a tuple is linear, it becomes a subspace. Okay, and last but not least, well, it kind of goes back to the one before and generalizes something. So this spans v if and only if, well, gamma of v1 through vn is surjective. So this is a consequence of what we've seen just right before here, together with what we proved last time, that a linear map is surjective if and only if the image is everything. Yeah, so here now, if this spans v, that means the span of this is equal to v. That means the image of gamma is equal to everything, which means that the image, that means that gamma of v1 through vn is surjective. So this last thing here really combines a lot of things that we've done before. Okay, great. So now we're coming to the last result of today's lecture. And this is something that seems rather trivial, but it's going to be used a lot throughout. And since I told you can only use things that we've actually proven, we have to do this. Okay, so what do I want to say here? let's start with a vector space over R, and we take an n tuple of vectors. Then we've seen already that span of v1 through vn is a subspace. It should be obvious that it contains v1 through vn, but what I'm claiming here now, that it's the smallest subspace that they contain it. So what does that even mean? That means every subspace of V that contains v1 through vn also contains the span of v1 through vn. And I think it's always a good idea to kind of think about the theorem, what you want to prove first and why this should be true, or what's the intuition behind before you really want to prove it. And so what's the intuition here? Well, if you take a subspace of V that contains v1 through vn, well, we have shown then that all linear combinations of v1 through vn should be in that space. Yeah, this was a result we have shown in a previous lecture. Well, and the span is just the collection of all these, and this is pretty much the result. So it is clear that, that span of v1 through vn contains v1 through vn as vi is equal to 0 times v1 plus 1 times vi plus 0 times vn, yeah? So I can always write a vi, obviously, as a linear combination in v1 through vn. And span of v1 through vn is a subspace as mentioned above. So it is left to show that any subspace U of V that contains v1 through vn also contains the span of v1 through vn. Okay, well, we want to show span of v1 through vn is a subset of U. Great. How do we do that? Let U be in the span of v1 through vn. E dot, there are lambda 1 through lambda n in R such that U is equal to lambda 1 v1 plus all the way up to lambda n vn. Great. And now we go back to theorem 3.9. Let me remind you, theorem 3.9 said that if you have elements in the vector space, so in this case v1 through vn, they're all in U, then also any linear combination of them is in U. So E dot U is a linear combination of v1 through vn, as v1 through vn are vectors in U, and U is a subspace of V. Theorem 3.9 yields that U is in U, and this finishes the proof. So thus the span of v1 through vn is a subset of U. Okay, so this will be an important tool later on, and since it has to do with span, we did it right here. This is all for today, and I hope to see you Wednesday and answer all your questions.